G'day Bifrosters. Let's do some scattering. We're going on a journey into scatter points, which is Bifrost's scatter pack scattering node, and it's the main one. We're going to use it an awful lot, and we're going to use it for a lot of very interesting things. But to start with, we better find out how it works. So what we need, before we need anything else, is we need some geometry to scatter on. There's some stuff we'll be doing later that doesn't, but for now, we're going to need something to scatter on, and I have this piece of geometry here. There it is. Has a bunch of points. And at its most basic, scatter points. So at its most basic, what scatter points does is exactly what it says. It scatters points. So as you can see, I have scattered a bunch of points on this geometry. To be absolutely precise, I have scattered 1,000 points on this geometry, and I have done it in a random fashion based on the number I'm giving it here. That's as easy as it gets. That's the basic scatter. I'm going to scatter a random amount of points on an object with some rules. The easiest way to go through this with you is to do something with it. But before I do that, what I'm going to do is take you through the settings. And we're going to go through the settings fairly quickly, but hopefully quite thoroughly. So bear with me while we do that. And if you already know how it works, feel free to jump ahead. We're going to start off with this one and this one. So the amount is fairly easy. Before we go any further, what I'm going to do is I'm going to add a watch point here. And this has all kinds of advantages, mainly to show us what's going on. So, as you can see, I am scattering 1,000 points, and I am getting 1,000 points out. So far, so good. 500 points, get less points, 500 points. Change the seed, still 500 points. Now 2,500 points. This all makes a lot of sense. The thing you need to realize is that it makes an awful lot of sense until you change this. So, right now we are scattering points randomly. And we are scattering lots and lots of points there. 25,000 will do, or 250,000. It's very, very fast. That's the great thing about it. Let's go back to 2,500 for now. And there we go, 2,500, 2,500, same as before. What this guy is for, the max number, if I did scatter 250,000, but set this to 100,000, you can see what's happened to the count. I'll drop that back 1 to 25,000, and we'll drop this back to 10,000, so you can see the difference. So this is limiting the number of points, the maximum number of points you can scatter. Its default is 1,000,000, and what it's really for is not for limiting the points. I mean, you're obviously typing in the amount of points that you want when this is set to random. What this is for is the other two in this drop down. So getting a little bit ahead of ourselves, but what we have here is random. Random scatter, picks a point, it's based on a seed, it's a random number generator across this piece of geometry. Blue noise. And what I'm going to do there, I'm going to drop the point. You can suddenly see what blue noise is doing. So what blue noise is doing is trying to fit as many points as it can in here with enough spacing between them. So as far as possible as they can get from each other. You can read about it here in the info node, which I love info nodes, they help me all the time. Blue noise gives you a blue noise distribution. This is also referred to as a quasi-random or low discrepancy distribution. It provides a more even distribution with points more equally spaced. So the good thing about blue noise is, as well as points equally spaced, they're still reasonably random. They're not in a grid or anything, but they're evenly spread out across the geometry. And as you can see, I've got 2,500 points in my amount, but only 2,000 points here. So what that tells me is that 2,000 points is all that Bifrost could fit in this geometry even. The next one is blue noise maximal, which is a lot more computationally intensive, and it gives very similar result to blue noise. But what Blue Noise Maximal does is it tries to deliver the most efficient scatter on this mesh. I believe this is full-on plus on disk sampling. A Wikipedia page for that is good if you want to have a look. And like I said, it's very, very computationally intensive. So I don't tend to use it much. The great thing about both blue noises is what you're looking at from the top down here is a forest. If you imagine these as trees, the way trees work is trees have leaves and branches and things that come out. Those branches and things tend to block the light coming from the sky and the sun. So for some radius around the tree, nothing's going to grow because it can't get any sunlight. But if it's far enough away from the other tree so that its branches get the light, then it's going to grow. So blue noise is your absolute go-to if you're scattering a forest. So that's the 3 scatter modes. Let's work on the amount mode. So right now it's set to number. What this is saying at the moment is I want this many points. Yeah, there's 5,000. There's 500. There's 2 other amount modes here, and this is where max number is going to come into play. So I'm just going to take this down to 5 and switch this to density. So that's given me 8,742 points with a density of 5. Because if we look in the info node here, density generates amount locations per unit of surface area, strand length, or volume. So I happen to know that this plane is, I think, 40 by 40 units. So it has an area of 1,600 units. And I would bet that if we pulled up a calculator and multiplied by 1,600 by 5, we get about 8,000. Here we've got about 8,742. So you can see how that's working. 5 points per surface area. And this is where the max number comes in, because if I take that to 10, it doubles it, 16,000. So if I take it to 100, 174,000. If I take it back to 1,000 in the density, there we go. Our max number has kicked in and limited it to 1 million. That's just one thing that it's good for. The other one is radius. So the way radius works is that it's trying to keep these at least 1 unit apart. Check the info for that. Generates locations that are spaced at least 2 times amount units apart. Amount units is this. 0.5, I get more. 2, I get less. So it's trying to place them twice that amount apart. If I have a radius of 0.1, I got 30,000 points. Now just imagine if I had a radius of 0.1 on a 400 by 400 unit grid. Then you would start to run into things like billions of points. If I had a radius of 0.005 or 0.001, because that's the density I needed on my scatter, you're going to end up with billions of points. And I don't know what your machine is capable of, but mine would crash really, really quickly. So that's basically how all of this section, the scatter settings, work. And then what you're going to do to set up your scatter mostly. Let's take this back to number. Take this back to 2,000. 2,000 points scattered randomly on this guy. You can even go to blue noise. Get it more of an even scatter. That explains the scatter settings. As we go through all the scattering we're going to do, you'll find that this, or something like this, is used over and over and over again. Scatter mode, the amount, the seed, and a max number. Just for safety. The next thing we need to talk about is culling. I'm going to set this up to 1. I'm going to cull overlapping points. There we go. No, it's not blue noise, it's random. But any point that is closer than 1 to each other has been deleted. You can see that if I turn that off, my count goes back to 2,000. Turn it on, count goes to 234. Obviously, if I drop this number, drop it again, then you can see how that's working. Now we need to talk a little bit about density weights. And density weights is a really, really handy thing. At its most simple, what it's doing is it's saying that for every point, and in this one we've got 1,366 points, for every point I'm going to assign a probability of existing between 0, which is it won't exist, and 1, it will exist. Let me show you that. Let me just plug in 0. No points. 0 count. As we bring up that value, so it's 0.25, and that's 0.5, and then we go all the way up to 1, or just over, you can see our points climb back to 1366. So this is not saying, unless if you make this an integer and make it 0 or 1, then yes, you've got, I'm not going to be scattered there, I am going to be scattered there. Then that becomes a switch, becomes a Boolean operation. But the really nice thing is you can go in between that and it's treated as a probability. And what's more, you don't have to just plug in a single number for every single one. So what I can do is I get point count and a random value array. Plug the count into the size of the array, geometry into our plane coming in. So this is going to give us 1600 random numbers between 0 and 1 in an array. And then I can plug that into my density weights. And now I've got a random chance. And you can really see this if I push this up to 20,000. And let's turn off color overlapping. So you can see generated random all the way through this based on this random value array. So that's pretty good too. And we're going to be using this in just a second to do something fairly interesting. Also, as of Bifrost 2.3, if you don't have it, please go download it now. It's awesome. You can plug a field into that, because the thing I haven't been telling you is density weight, it's going to take anything that will deliver it a float. And a scalar field, this doesn't work for vector fields, but a scalar field will deliver a whole bunch of floats. So if I plug in this fractal noise field, like so, and you can see what's happened. And the lovely thing about fractal noise fields is you have a bunch of settings here. So I bring down my frequency, you can see what's happening. If I change the frequency ratio, then you can make it more complex or more simple. I can change the number of frequencies. I can change the magnitude of the field. So it's scattering more and more and more inside those parts of the field that are 1 or over. So density weights is great and a good way to decide what points are being scattered and what aren't. And then your density weights mode, you can change it from random to distance based, and you can see the changes it's made there. So looking at the info and the culling, random randomly deletes points per that probability. Distance based deletes points that are too close to other points. Looking at that also by that probability. That's the difference between those two, and it works, of course, if I go to blue noise, scatter those points as evenly as I can, put in the fractal noise field, and I can, again, do that kind of thing with it. It all helps in designing your point scatter, designing the way that your scatter looks, and as I'll show you in just a minute, with a bit of logic and a few curves, we can do something really, really interesting with that. But I'm in the node at the moment, so we'll keep going. Properties. Properties is important. What the properties are doing is that it's scattering a point at a location. Let's pick a point. Let's pick this one. So when it scatters this point, it checks their location on the object that you're scattering on. And it's at this point, it's picking up the point normal of it. I can add more to this list. I can put in point color, because I happen to know, just to put a watch point down to see what attributes are coming out of my plane mesh. I got that wrong, I'm sorry. I have a color, but I have a point normal as well. So let's change that point color to just color. And so now what I could do is I can go to my point scope, and at the moment it's the point normal that's being used for color. And I can illustrate the transfer properties here. If I take out point normal, they go black. They don't have anything to display. If I go back to my point scope and change point normal to color, they look like they disappear. And they look like they disappear because they're the same color as the plane. They're picking up the color of the plane when they're being scattered and transferring that attribute onto the points that it generates. So if I want to get the point normal back, I'll just have to put point normal back in there. Come back over here, change this to point normal 2. And then we've got our normal colors back. So what can we do with this? Well, it turns out you can do an awful lot with this. And let's start doing some stuff. As you might have guessed by the different colors of the normals, this is not a flat 2D mesh. This is a 3D terrain mesh. So just to have a quick look at that, I'm going to turn our mesh back on, and I'm going to drop the number of points we've got. So there we are. It's 2,000 points. Let's turn our lighting back on, and you can see that that's kind of a nice terrain-looking mesh. It's really just noises displacing the plane, but it'll do. It'll do. And the nice thing about point scopes is I can change this to point normal, turn on enable arrows, make that just a little bit bigger, and you can see that the points are picking up the surface normal from the geometry that's being put into them. This becomes quite important later. Well, it becomes quite important now, actually, because what we're going to talk about now is the last thing, the orientation of the property. So if we take a look at what's coming out of our scatter again, I thought I had a watch point, but I've obviously gotten rid of it. Let me get our watch point back up. You can see I've got point orientation, and point orientation is pretty much which way this point is pointing, which way it's rotated, is the rotate information on that. And scatter by number is generating that for us from the geometry. It's using the point normal and the UV to generate the orientation. This mesh doesn't really have a UV, so having this set to UV isn't really going to help. It's not going to generate, it's going to generate the orientation setting, but the orientation setting won't quite be right. If I change that to connectivity, then and we can check the info on this. There we go. Connectivity computes the tangent based on the edge flow of the underlying mesh topology. So basically it's taking the edges around the point and working out what the tangent is based on that and the normal. It's vector math, it's trigonometry. Which if I haven't done a video about, that's only really because I'm too scared to, and I should probably get onto that. The last one is prioritize normal. So prioritize normal controls what happens when the normals and tangents are not orthogonal. When prioritize normal is true, the y-axis of resulting orientation is exactly aligned with the normal, and that's what we want. So if you were to imagine some axes coming off these points, this one would be the y, then you would have an x and a z. And those two are calculated using the underlying edge geometry and a normal. So by doing it this way and setting this up and making sure we have prioritized normal on, set orientations from geometry on, then we can get an accurate orientation. That is the first look at scatter points node. That is the bit where we go through all of the settings and explain them. Let's now do something with it. So let's do something with these points. I'm going to change my amount mode back to number and change my number back to 2000. So actually, I'll just set it to 0 for the moment so we have no points. So just looking at this terrain, what I think I'd like to do is I would like to scatter some rocks around this. And this being either a very out of scale puddle of mud very close up on a beach, or it's either that or it's some mountains from fairly far away. Either way, when the world scatters things, the world has to worry about things like gravity, which means that if I put a rock here, it might sit in that little indent there. You can sort of see it. It might just sit there. It might not. It's far, far more likely to roll down the hill and end up on this plain area here. So what we're going to do is we're going to use some curves to make sure we only scatter down here. And we're going to use our density weights to do it. So let's add our points back. We're going for 2,000 points. And I'm okay with them being the color of the normals. We're going to change that in a minute. So what we're going to do first thing is we're going to build something to work with our density weights. And I'm going to use the points from the plane to do it. So what I'm going to do this time is I'm going to get the point positions. There we are. I have the point positions of every point on this plane. Not the points I've scattered, they're coming out here. But every point on this plane. What I'm going to do is I'm going to split that up. So I'm going to do a vector to scalar. Vector 3 to scalar to be precise. So now these are the three elements that make up the position of each point, the x, y, and z element. And what I'm going to do with these is I'm going to take the y element here and I'm going to get the bounds of the array. And what that means is that this is the X and the Y and the Z element, but they're all coming in from this big array of 1600 points that are coming in off the plane. So this is all of the Y components of those points. And what the array bounds does is it gets me the minimum number and the maximum number of those points. So the minimum Y and the maximum Y. And then I'm going to take that and throw it into a change range. So I've got the minimum bound to the start and the max bound to the end to plug the Y into here. Now why am I doing this? Well, what I'm going to do is I'm going to change whatever this is from, if we go to our side view and turn on our grid, you can kind of see that they sort of start at about -0.5 and they kind of go up to 4. So they've kind of got a spread of about 4.5 in the Y. I need to take that and remap that 4.5 down to 0 to 1, which is what I'm doing with this change range node. And the reason I'm doing that is we're going to do pretty much what we did before. I'm going to set a geo property here. Give it a minute to have a think. And the property I'm going to set this time is point color, because this is going to be quite good to demonstrate what we're doing and to show us what we're doing visually as we go along. Just turn that grid back off. So I'm going to set the geo point color. The thing is that color is made up of RG and B values, and sometimes alpha. But I'm just going to use the RGB for now. So we'll go to MathFloat 3. It's going to have a little bit of a problem because its data is a float and its default is a MathFloat 3. So we need to change the data as well. So what I'm going to do is a scale it to vector again. Scale it to vector 3. And this time what I want to do, because this is going to become a color, is I want to put 3 of the results of these arrays. So what was Y is now X, Y, and Z, or as they're going to become colors, red, green, and blue. So what this should produce is a grayscale color for me. Now nothing's going to happen just yet, because I need to do some adjustments here. First thing I'm going to need to do is I'm going to need to transfer the point color to the points. And we did that before and they came out grey. But they won't come out grey because what we're doing here is setting that point color to whatever comes out of here before it goes into the scatter. So because it's before it goes into the scatter, I'm setting the point color of the plane rather than the points, and then I'm passing that attribute and transferring it to the points. So now if we go back to our point scope and change point normal to point color, now you've suddenly got a black and white version that's reflecting the height, which is exactly what we wanted. So what this is basically doing is it's taking the height, the Y value, so it's the height, I'm going to call it the height. It's taking the Y value of each point on this plane, squeezing it down to from -0.5 to 4, or whatever it was, down to 0 to 1, and then putting it all out into a vector, which is becoming a color for us. What we want to be able to do is adjust that. So just after making it, I'm going to break those connections. I'm going to move these guys along a little bit, and I'm going to put in an evaluate F-curve in between these two nodes. So we're going to put the result, our 0 to 1 result, into the X, and our Y out to our colors. And what this is going to let us do is adjust this. So at the moment, I'll just pop that out. At the moment, we're getting a linear curve. So if you have a look at the F-curve node, you've got X as the input and Y as the output. And this is the X-axis and this is the Y-axis. And that's exactly what we're mapping. So the X is what's coming in. So at the moment, if something is coming in at 0, it is also going out at 0. What ends up being 0 after being remapped in this change range, which is at the lowest point of our terrain, that's coming in as a 0 and it's going out as a 0. So we'd have to go and find the blackest point in here, which is probably one of these, and that would be the lowest point on our plane. Now, same at the other end. What's coming in at 1 is going out at 1. So the brightest point, which I'm guessing is probably that one, because it looks like it's higher than everything else up there, possibly that one. So that's coming out of our remap to 0 to 1 as white, as 1. So that's where it's coming in, and that's where it's coming out. So it's going out at 1. Showing you real quickly how curve works, if I reverse this curve, then you have the opposite. You have the highest one is black because it's coming in at 0 and going out at 1. And you have the darkest ones, you have the lowest ones on the terrain are white because they're coming in at 1 and going out at 0. Which means if I start pulling this back, I'm essentially making a height threshold by colour. And the colours are really just there so I can demonstrate this. So now what's happening is that anything that's coming in along the x-axis at 0.2 or greater, so 0.2, 0.3, 0.4, 0.5, 0.6, all the way up to 1, all of those are coming in at those numbers, but they're all going out at 0. What it's basically saying is that anything that's higher than 0.2 on our input is now to go out as black. And that's what we get here. So if you were to do the measurements and take a look at this side on, and we need to find this value and find out what 0.2, what a fifth of what 0.2 is of that value, then you could probably map where everything started changing. But I prefer to put colours on the points so I can have a visual look at what I'm doing. So as you can see, what this is doing is it's highlighting all of our low-lying areas in white. And that's precisely what I want, because what I want to do is just scatter on anything that has the appearance or is low, is flatter, is not mountainous, anything that's lower down on this plane. So this is pretty much giving me exactly what I want right out of the box. And the really nice thing is that if I take what comes out of that F curve, which remember gets changed to 0 to 1, and then it gets adjusted by this curve so that, see there, if I zoom that out, you can see here the 0 coming in at 0, going out at 1. It's the low-lying ones coming in at 0.1, going out at about 0.5, which is kind of these grey ones here, and coming in at 0.2 is going out at 0, and anything above that is also going out at 0, and these are these high ones. So if I take the output of this curve and just plug it straight into the density weights, that's what I've got. So remember, the density weights are the chance of something being scattered at that point. Yeah? So, because I made a whole bunch of stuff black, there is no chance of anything being scattered at that point. So all I'm getting is the low-lying stuff, which is brilliant. That's precisely what I want. That's exactly what I'm after. And the really nice thing about this, I'm going to wrap all of this up in a little compound. So we'll just do this and we'll group it. That we'll call that height. And coming into the height is the geometry, and coming out of the height is the color and the density weight. Why don't we just call this scatter chance, so that it's a bit more easy to remember what that is. So far so good. We've got our scatter working, we've got points low-lying. Let's see what else we can do with this scatter, or what else this scatter enables us to do. So, time to get some rocks. Well, to scatter rocks, we're going to need a bunch of different rocks. So let me just really quickly make that. Throw down a for each loop. And very importantly, I'm going to set my iterations to 1, just to start with. Just so we can see what's going on in there. And I'm going to, oops, let's jump in there. First thing I want is a mesh sphere. Great mesh sphere, just like that. We're going to give it a few more segments so it doesn't look quite so bad. And I'll pop that into the output. And then if we go up here and just quickly throw it in the terminal just to see what we're doing. Plug that into the proxy, and here's a sphere. So this is going to become our rock. This is the reason I set my iterations to 1 to start with, so that I'm just looking at one of them. And what we'll do here is we will displace points. And we'll throw that out to, we'll pop that out here as well. And I'm just going to put down a fractal noise field. plug that straight into the displace points. So we're getting something slightly spiky, which is really what I wanted to avoid. So what I'm going to do to help with the spikiness is I'm just going to shuffle down the frequency a bit and also pull down the frequency ratio while doing something like that. Just it doesn't have to be a really good looking rock, it just has to be a rock shape. And just to make sure that we've got a different rock each time, and these are very rounded rocks, we can say that they're river rocks or something, but I'm going to plug the current index, which remember changes every time we go around the loop, into the seed, so that our rocks, which are now looking very interesting, acceleration have gone up to 2, we'll just take that back to 1. I mean, if you wanted to add some detail, a really quick and easy way to do that is to duplicate this field. You can leave the seed the same for this, really, but it does pay if you want to. You can increment that by 1 just so it's got a different seed. And what we want to do is just a classic little bit of fractal Brownian motion here. What I want to do is I want to make this a lot more frequent. So it's about 0.25. Let's go 4 times that with frequency 1. And then we'll add these two together. And you remember I went 4 times that. So this is about 1. Let's take the magnitude down to 0.25, which is about a quarter of the magnitude. And we'll just plug that in. And so what that's going to give us is just a little bit more surface detail. Really. Something I'm going to check is what happens if I do that. It's looking a little better, a little bit more rocky. So I think we'll go with that for our rock. And we can take a look at what, so if we take this, say we want 10 rocks, it's going to generate 10 rocks for us. And they're all going to be on top of each other. But I can see what each one looks like by just changing the current index, I think. Other way around, sorry. So iterations to 1. So we're just seeing 1 at a time. But I can change that index to take a look at what's going on. And those are the rocks I'm going to get. They're pretty weird and wonderful, but they are also quick. So let's change our current index back to 0. We've had enough previewing. We'll change our iterations back to 10. As I said, not the world's prettiest rocks. I wouldn't want to render them close up, but plenty good for our purposes. So we get up out of there. So we've now got what essentially is a rock generator. Be a bit kind to ourselves and change this to something like number of rocks. All good. Let's just turn this terminal off for now. Make sure that this is going to the output now that we've had a look at it. Delete the terminal. So what we're going to do, turn these guys back on. So there are the points. They've still got my nice colours on them. Remember, all of the high ones have been deleted. I might just change this point scope and change the default size to 0.05 so they're a bit smaller, not sort of taking up so much space. So what I'm going to do is I'm going to instance these rocks onto those points. We'll do that. We'll create us some instances like that. And let's put the rock generator rocks into the instance geometry. And then we'll take that out and let's plug that into the proxy as well. So we've got the rocks in the same place as the points. And now we've got a field of rocks. As I said before, they're not the most pretty of rocks. We're going to need to do some things to them. And the very first thing I want to do to them right now is I want to change selection mode from sequential, where essentially it's going, I have some points. How many points do I have? Well, I have 366 points after all of our culling. So at point 0, it takes the first rock in the sequence. Remember, there is 10 rocks, so this is taking rock 0. And then at the second point that's coming in, it's taking rock 1. And the third point, it's taking rock 2, and all the way up to rock 9 when it switches over and goes back to rock 0 again. What I would rather do is randomize those. Bang. So the really nice thing about the instance random selection is that if I had 10 rocks that ranged from very rough to very smooth, or very small to very big, I could select the probability on a curve of what rock would be scattered the most. So, and again, it would be, these are the rocks coming in, and this is the probability going out. But because they're all pretty much the same rock in our instance, we'll do this a different way. I just wanted to mention that because it might come up later. There may be a test. So, first thing I want to do is make those rocks a lot smaller. A lot smaller. And the way I'm going to do that is I'm going to randomize point scale. Give it a minute to sort its life out. There we go. And you can see that something's happened already. So all of our rocks are quite deliberately left at a mesh sphere radius of 1. So if I set this to minimum 1, maximum 1, that's pretty much the size they are when they're created and the size they're coming out. I want them to be quite a lot smaller. So let's try 1/10 of that. So now we're getting something a little better. These very small rocks down here. These guys are still a bit bigger. Maybe I don't want them to go past 0.33. Now they're a little small, so I can just drag this up until I get something I like the look of. Like that. Which is great. And of course I can change the seed. And they're all looking a bit odd at the moment, but we're going to get onto that. They're all sort of standing on their noses, sticking into the ground and hovering and doing all kinds of weird and wonderful things. Now just remember that Bifrost is non-destructive and it's procedural. So if I go in here and I change the seed, I can't change the seed, I'm using the seed for something else. But if I go in here and change the frequency of these rocks, you can see that every single one of them changes. So we'll take that down. We'll take the frequency ratio. It's a bit puffy now. We'll take the frequency ratio to about there. And it's happening to every single rock. And also maybe I think that they're just sitting a bit too high. And that's because I've got base to pivot set, which means that the pivot point of these rocks are set to its base. If we turn that off, then it's going to be set to their center. So suddenly we're looking at something a lot more like a field of rocks. And they're only turning up in the low-lying areas, which is great. It's really, really good. Cool. And again, what's also nice is I can go even further back in the graph to back into our height node. Let's just lay that out real fast. What I'm going to do is I'm going to take the evaluate curve and I'm going to put that out into the input so I don't have to keep diving in here. And then I can go to the curve on the input node like this, and it's still a linear. So it's still just going, remember this is where the rocks are and where the rocks are and where the rocks aren't. So I can get some change out of that by changing that to a Bezier curve. And now they're reaching a lot further up the hill because this has reset itself back to 1. The position we want here is 0.2. There we go. And now if I just frame that, I'll pop it out too. We'll just frame that curve. You can see that it's probably going to need a little bit of adjustment here. Just a little bit. To not have quite such a precipitous drop. It's looking pretty good to me. I mean, the rocks are a little big for the landscape. If I was to put my VFX supervisor hat on, I'd have some things to say. But as a demonstration, it's working very well. Okay, so what now? All of these rocks are pretty much facing the same way. They're nice and random. It's not amazingly obvious that they've been cloned. You can find them. Those two are the same rock and they're pointing exactly the same way. They're also both sitting a little bit high. So the next thing I'm going to talk about is rotating these instances. Now, this is where the point orientation comes in from earlier. You remember here that, where's my watch point? It's gone. I'll just go out on this one so we can have a bit of a look off to the side. So remember we've got a point orientation, and this is telling the instances through the points what orientation to be. So it's which way these rocks are rotating. So I can of course put in a randomize point rotation as well. And you can see that they immediately rotated. Random fashion. Now, what's going on here is minimum radians and to rotate and maximum radians to rotate. Most of the rotation is being done on the y-axis, and you remember when we scattered the points, we had the y-axis shooting straight up. So that's why we did that. So now we can get things to rotate around like this. So I'm just going to save this for a minute, and we're going to go make a new file. Yeah, it's just new. And what I'm going to do for this file is I'm going to actually load something from the Bifrost browser. I'm going to load it from Scatterpack. I'm going to use the scatter orientations. Import that. There we go. And so this is illustrating it really, really well. And what's really lovely about it is it's exactly what we've just done. Here's some geometry. Here is a scatter. Here are some instances on that scatter, which are these axis objects, which is basically just a series of cubes and colors. So I can do exactly the same thing here by taking the points. I can go to randomized point rotation, plug it into the right thing. I plugged it into the wrong thing there. Plug it into the right thing, and you can see that it's randomized all of these, but mostly around the Y. I can even take that out. You can see them just flatten out a little bit. So now they're all randomly rotated, but only around the Y axis. So to illustrate that even better, let's get rid of that. Got another good node here, which is just rotate points. Get that done there, that in there. I'm going to move this axis mesh up for now because we're not going to change that. That's very handy to have. So I have rotate points here, and what rotate points gives me is it's asking me for an axis, and it's asking me for some radians to rotate. So what I'm going to do is I'm going to give it a couple of value nodes, like that and that. I'm going to make one of them into a vector. 3 to be precise, and I'm going to put the Y value of that vector to 1. So this is the axis we're going to use to start with. This is the Y axis. We'll plug that into the axis. All good. And this is going to be the amount we rotate in radians. So let's plug that into radians. And you notice there that this is also an interpreted port, because I can plug a single float into it and it's working fine. So now if I come in here and I just start rotating this, you can see that it's rotating, but it's not rotating around the Y-axis, is it? Well, actually it is. It's rotating around the world Y-axis. And the reason for that is I'm not rotating in local space, I'm rotating in world space. So it's rotating everything around this axis. So let's just go back and reset this. I'm going to rotate points and I'll turn on local space, and then when I start changing this value, it's a little fast, but you can see they're rotating around the local Y-axis. They're stacking it like that. And this works all kinds of other ways as well. Reset that. Well, it works the same way, but it works on the other axes. So if I go to my radians now, I'm rotating around the X-axis locally. Like so. And again, if I turn off local space, I'm going to get something odd because it's rotating around the world axis. Like that. Again, if I change to Z, start gently playing with our radians, you can see what that's doing as well. That's rotating around the Z axis. So when I put on a randomized rotate, what I'm essentially doing is rotating points like this, but I'm putting in a random value in radians for the Y value in my randomized point rotation. So that's just a quick demo to let you know, so let you see how this is working. And this is not a perfect sphere, it's lumpy. You can see that they stick to the surface quite nicely. And all of this is because we are making orientations based on the geometry, based on the point normal and the connectivity. So this is literally just a normal scatter like we've been doing. So this is scattering by radius. So if I make that just a little bit smaller, we'll get more points. But these points are random. They were blue noise before. It's all going to be quite happy to just work the same way. Just rotate nicely, whether it's random, whether whether it's blue noise, whatever. Okay, so let's go back to our file. So now we've got a few more things we can use on our rocks. I quite like having a randomized point rotation. But if I wanted to adjust the rocks as well, I could also put in a rotate. Maybe I'd need to spell it properly. Rotate points in here. And again, I could make an axis and radians, and I could rotate them, they'd all rotate at once. But so if I could throw down, I am going to do it, I'll throw down an axis. Let's make this a vector 3, and we'll plug that in. Plug this into our radians, and we'll do it on the y-axis. Remember, we're going to do it, make sure we do it on local space here, and get some rotation going. You can see the rocks are all just happily rotating away. They're rotating in different directions because I have a randomized point rotation here. And this is stacked on top of that. But you can see that both of these, well, all three of these nodes, point scale, point rotation, and rotate points, have weights. And these work very, very similar to density weights. So we can, if we want to, and I think we want to, we could use our point scale here. If I wanted to take a quick look at the point scale, let's throw that into an output node so we can get a reading off the watch point. So at the moment, our point scale, its minimum is 0.09 and its maximum is 0.4 because this is what we've set our min and max to in the random. So what I can do is very, very similar. Just delete that now. What I can do is really similar to what we did with the weights, is I can take the point scale, and this is an array with a point scale for every generated point in it. Take this out, I can split this up, vector to scalar, like so. Because I don't need all three, I just need one of these. And do our neat trick with the array bounds again. And the change range. And the array bounds tricks is just so that I don't have to go back and keep referring to what I've set these to in the random value. It's going to work it out from the array. And I can pick any one of these. In fact, I can pick two different ones like that. Because the point scale is going to be the same across all three components. So that goes into start, that goes into end, and then in our change range, we want to make it from 0 to 1. So it's just remapping whatever those point scales are to 0 to 1. And then I'm going to take that, and we'll just tidy up a little bit here. I'm going to take that and put it into the rotate points. Well, I'm going to put it into the rotate points. Weights. So if we just come to the rotate points, we go to the info, and we look at weights. So this is a proportion of the rotation to apply. Rate of 0 gives no rotation. A rate in the range 0 to 1 gives a rotation by a proportion of the given angle. The given angle is pretty much whatever the randomized point rotation and this value here is. So that's what we're looking at doing. We're going to use 0 to 1. We can give 1, which will be giving exactly the angle. Above 1, which is going to be greater than the angle, or below 0 will give a rotation in the opposite direction. So I could change this to minus 1 to 1, even, and then pop that into the weights there. You see they just jumped a little bit. And that's because now if I change this, you can, maybe if I didn't change it so quickly, go back to 0. So if I start changing this, you should be able to see that the bigger rocks are going to rotate faster than the smaller rocks because we use the scale to generate our weights. See how that works? So the bigger one is getting the most rotation and the little ones are getting the least. If we wanted to switch that around, we just need to switch those two numbers. Okay, last thing, and then we're pretty much done with scattering 101, or scatter points, or whatever it is we're doing. Just an example to show you what we're doing, really, is I don't like the way these guys are half sort of hovering up out of the plane. There's a few ways I can fix this. There's some complicated ways, like I could basically raycast out from each rock onto the plane, and then as you get closer to the rock, the plane would lift up a little bit, so it looked like they had sort of almost cratered into there. What I'm going to do just for speed is I'm going to do point translate. I can also do a randomized point translation, but I'm just going to do a translate points. And again, you've got weights, you've got local space, you've got all kinds of things. And what this is doing is it's asking me for a vector. So by putting in a vector here, I'm applying this to every single rock, like this. It's going to lift up and away. So if I set that to 0, they'll be wherever they're being scattered at. And if I set it to -1, it's going to drop them all. Now that's a problem because my little ones are now all floating underneath. So I think we're going to do the same trick with the weights. If I take this, copy and paste it. Remember, this is the scale, so this is giving us the bigger rocks are the max bound, and the bigger scales are the max bound, and the smaller scales are the minimum bound. If I go to this and I just say, like, okay, 0. So I don't really want to move the little ones at all, very much. I just want to move the big ones the most, like this. Take this and pop it into the weights, like that. You can see a whole bunch of them pop back up. And if I go back and just set it to 0 and start changing that upwards, what you should see is the biggest rocks start to move first, like that. So we want it to go the other way, obviously. So we want to just drop these big rocks down, and down and down and down. We're into the negatives now, and I'm just doing this by eyeball because it's nice and fast. I don't want to lose too many rocks, but we can get some of them like that, that'll be fine. And again, we can do it. We can adjust this with an evaluate F curve. So when you do that, it always pops itself into the F curve and you have to change it, which is always fun. And we just put the weights into there, which is fine, which is great. So remember, it's still doing it by this, but we can now have the ability to edit this curve like that. So now anything coming in at 0, it doesn't start coming up until a little way along. It's smoothing out this curve. So rather than just straight out linear, it's smoothing it out into a nice curve. I can change that. I can say, like, well, no, I don't really want you. I just want you to ease out so the bigger ones get more. Like that. I can take this guy. I can just move that the wrong way. So we can take this and just pop it up a little bit. So it's 1.2 times whatever's going on. And I can say, you know, I want kind of more of you. And you can kind of see the rocks just shifting as you work that through. So that's looking a bit more like a field of rocks. And there are some just hovering down underneath there, which I'm not too worried about right now. And let's quietly just turn off our point scope for a second. So I'll just delete that. Points go away. So now we've achieved our goal. We've randomly scattered some rocks on the lowest parts of the geometry. We've done some adjustments because it didn't look very good. And we've still got the ability to make more adjustments should we want to. I can lift some of them up. That's great. So yeah, that's pretty much it. That's the example and a little bit of a deep dive into what you can do with the scatter points node, including transferring properties and then using those properties later on. And I mean, we're still transferring the point color from the height. I can transfer that point color onto those points as well. So we talked about let's get rid of the instances for a little bit. There we go. It's a little harder to see at this stage of the game. So I hope this has helped you with scattering a little bit, cleared things up a little if they were confusing to start with. Yeah, so I'll go away now and let you get on with your evening. And yeah, thank you very much. I hope it helped.